since the beginning of nuclear science. It's been a long-standing project even to establish what isotopes are there in nature and what combinations of neutrons and protons are actually possible.
Answering some of the very simple questions we can answer about our world, what exists and what does not exist. It's a long way to prepare such a discovery. It's not just happening by happenstance that you stumble over something and say, oops, it's there.
The three rare isotopes that were never seen before that we discovered are magnesium-40, aluminum-42 and aluminum-43. And we ran for 5 days and we didn't see a single event. At that time we were pretty much convinced that there was nothing to get. And then on the 5th day, one evening, somebody at the main console saw one dot at the proper space where we would expect magnesium-40. We very quickly then looked at all the parameters and verified this is actually a magnesium-40 event. So it was a very exciting evening.
Any isotope that we might make here in the laboratory, we have to start from a stable isotope that we already have. By accelerating them and bringing them to a very high velocity in our cyclotron system, reacting them with another material and break them into pieces, and then identify each one individually with absolute certainty.
The really simple way we like to explain it is by saying that we measure pennies on a jumbo jet that's about to explode. And that's our analogy for it. What that means is that we weigh really, really small particles that are produced at the cyclotron here. And I say the jumbo jet's about to explode. What I mean by that is these very rare particles, isotopes that we measure here, often don't live very long.
One of the important features of being on the campus is that we always are interacting with young people, that we have undergraduate students who are studying physics maybe for the first time. And then we have graduate students who've completed their degrees and are now saying that they want a career in science.
And so we want to have maximum voltage or higher voltages so we can essentially repulse these ions away from the surface, but at the same time still guide them towards extraction and towards the experiment.
And we're really here running the experiments, turning on and off the cyclotron to a certain extent. The professors are there with us, guiding what we do, but we do a lot of it ourselves.
Then when I was shopping around for graduate school, I just joined the ranks, and I like it. I like my group, my advisor, and the resources. Yeah, they're quite large here.
When I talk to students that actually have a plan to continue a career in physics or even nuclear physics, I always tell them that this is the best place you can be. When I was a student here, I liked the atmosphere, and also it's one of the top 3 facilities in the world, I think, where you can do this kind of research.
There's just no better place to do basic research than on a university campus, which is equipped to house state-of-the-art facilities.
Nuclear scientists and engineers with their partners have transformed knowledge about the properties of atomic nuclei into tools for medical diagnosis and radiation therapy, detectors for national security, and numerous other remarkable technologies, many of them the results of work at this laboratory.
By developing better models to understand our world, we have a better chance to conquer the world in terms of finding ways how to improve it.
That's always the hope, is that somebody will take what you've done and do something better with it, building on it and taking it further. That's what science is all about.